Okay, so in the previous segment we looked at one specific example of a driven quantum system. Let us now look at some very general aspects of such dynamics. For this we again consider how the initial conditions of the state at some time t0 determine the dynamics of the state at any time t. The relation between the states is of course given by the Schrödinger equation, and as before, this is a linear differential equation. Therefore, the states are still related by a linear operator u, and this then defines the time evolution operator for this more general setting. So this operator plays the same role as the one that we encountered in the last chapter. However, it now depends on both times t and t0 independently. Nonetheless, this operator still displays many of the useful features that we identified before. For instance, when we equate the two times t and t0, then we obtain the same state on both sides of the equation, and therefore the corresponding time evolution operator must be the identity operator. So this relation must hold for all times t. And because for all initial conditions the quantum states solve the Schrödinger equation, we find an analogous equation for the time evolution operator itself. But note now that the time derivative in here acts on one of the two arguments only, so the other one is being kept fixed. Next we can solve the defining equation also for the initial state. This we can simply do by applying the inverse of the time evolution operator. But this we can also interpret as the defining equation with the times t and t0 interchanged. And with this relation we can then show that the time evolution operator remains unitary, which was of course one of the key properties that we found so useful in the last chapter. For this we first note when we multiply the Hermitian conjugate of the operator with the operator itself, then this definitely gives us the identity operator when we simply equate the two times. And then we check whether this relation is maintained when we change one of the two times. This we can of course do by taking derivatives with respect to that time. We then first apply the product rule, and in the terms we then identify the Schrödinger equation for the time evolution operator itself. We also encounter a corresponding equation for the Hermitian conjugate of the operator, similar to the dual Schrödinger equation that we have seen before for quantum states. But the two terms that we then end up with simply cancel, and therefore the object that we have taken the derivative of is not dependent on time. And so it remains fixed to the identity operator at all times t and t0, irrespective of whether these times are equal to each other or not. But what we have shown here is really just a definition of a unitary operator. And the main consequence of this is just as before, namely that the scalar product between two states evolving by the same Schrödinger equation does not change with time at all. So then, for instance, all states remain normalized, and when two states are initially orthogonal to each other, then they remain so for all times. The importance of this is often emphasized by calling this operator the unitary time evolution operator. We will exploit this property very soon, but let me first go through some methods to determine this operator. I mainly provide these for information and therefore without any further proof, but most of the resulting expressions are actually not that difficult to check. Well, first of all, we could set out to directly solve the Schrödinger-like equation for this operator, with the initial condition given as the identity as specified here. And one way to achieve this is to find a complete set of solutions for an orthonormal basis of initial conditions. We can then write the time evolution operator as this sum given here, which works out because all the states remain normalized and orthogonal to each other at all times. Next, let us consider the special case that the Hamiltonian, even though time-dependent, commutes with itself at any other time. In this case, we can directly generalize the explicit expression that we obtained in the case of a time-independent Hamiltonian. There, the time difference in the exponent is simply replaced by a time integral. This can be verified by making use of the series expansion of this exponential function. And based on such a series expansion, we can even give a completely general expression. So one can check that this indeed solves the Schrödinger-like equation for the time evolution operator. Here each term involves an additional time integral of the Hamiltonian. And the key point in here is that Hamiltonians for later times always appear to the left of Hamiltonians for earlier times. But one can also relate this expression again to the series expansion of an exponential function. For this we introduce the so-called time ordering operator. This operator simply takes any product of operators and places the ones for later times to the left of the ones at earlier times. And when one applies this to the series expansion of the stated exponential function, then one indeed recovers the general series expansion of the time evolution operator given above. Let me mention one more rather advanced method to determine the time evolution operator. This starts from the innocent observation that one can break up the time evolution into separate steps. When one iterates this, we obtain the following product representation. Note that in this product, order again matters. Once more, later times have to be placed to the left of earlier times. And so we can make sure of this again by utilizing the time ordering operator. And now we can consider, for instance, to apply this idea to the case of a point particle with a Hamiltonian as given here, and then break up the time evolution into increasingly smaller steps. For each small step, the time evolution operator can then be approximated by making use of only the first two terms of the general series expansion given above. And the result can then be rewritten in a very instructive way, in particular when one works in the position representation. In this basis, we call the time evolution operator also the propagator, and the expression that we end up with is a so-called path integral. In here, we integrate over all possible paths between the initial condition and the final condition. These are indeed all possible paths, not for instance just those related to the classical motion of the particle. However, each path enters via an object that is indeed known from classical mechanics. This is the so-called action, which in turn involves the so-called Lagrangian, as both specified here. Well, all of this suggests that finding the time evolution operator itself is generally quite a difficult task. Certainly more difficult in general than just finding one particular solution of the time-dependent Schrödinger equation. And nonetheless, we can make use of its general properties to find rather direct descriptions of the quantum dynamics. The first description is provided by the so-called Ehrenfest theorem. Here we consider directly the time evolution of expectation values. Let us write down the expectation value of some observable A, which can be obtained in the standard way. So this is time dependent because it involves the quantum state at time t. And using the time evolution operator, we can then relate this to the quantum state at another time, which for convenience we simply set to 0. And so this expression then depends on the time t via the time evolution operator itself. And so we can now make use of its general properties, and we do so by taking a time derivative of this expression. There we first apply the product rule, and then we make use of the Schrödinger-like equation for the operator u, as well as for its Hermitian conjugate. So these steps are very similar to the ones in the proof of the unitarity of the time evolution operator. But now the terms in the middle do not cancel. Instead, we can collect all terms as shown here. This expresses the result in terms of an expectation value at time t. And this expectation value is that of the commutator of the Hamiltonian with the observable A. Now here we assumed that the observable A does not have any time dependence itself, and that such time dependence can in principle appear, we have of course seen for the example of the Hamiltonian. But admitting such a time dependence simply gives us an extra term in the product rule at the beginning, and so we have this extra term here also at the end. And going back to the notation of expectation values, we can write the final result in the compact form given here. We will soon see how these expressions apply to a concrete example, but let me already point out a very general consequence of this. First of all, let us consider that the Hamiltonian itself is time independent and equate this to the observable in question. Then on the right-hand side we only have the commutator of the Hamiltonian with itself, and this of course vanishes. We conclude that the energy expectation value does not change with time, and therefore energy is conserved. But looking at the mechanism for this, we can then identify a general condition for other quantities to be conserved too. This requires that they do not have any explicit time dependence and furthermore commute with the Hamiltonian. And this suffices even when the Hamiltonian itself is dependent on time. And so we see that conserved quantities in quantum mechanics are related to the concept of simultaneous observables with the Hamiltonian. And whether such simultaneous observables exist is in turn often related to symmetries. For instance, for a central potential, the Hamiltonian is rotationally symmetric, and this means that it commutes with the angular momentum components, so that angular momentum is conserved. Now, to illustrate one more relatively general aspect and the general nature of these equations of motion, let us consider indeed the motion of a point particle in a one-dimensional potential. When we work out the corresponding commutators, we see that the expectation value of position changes in accordance to the expectation value of momentum. Furthermore, the expectation value for momentum changes in accordance to the expression given here. These equations specifically are known as the Ehrenfest equations of motion. And indeed they look very similar to the classical equations of motion. In particular, the rate of change of the expectation value for position just looks like the definition of the velocity in classical mechanics. And the equation for the momentum involves the negative of the gradient of the potential, so really just the classical force. But there is one significant difference, and this traces back to the nature of expectation values as averages. This means that we cannot exchange expectation values of functions with the function of the expectation value. And this applies in particular to expression involving the classical force. But only if we could exchange these two expressions, we would recover the classical equations. Now, to draw some more concrete conclusions from the Ehrenfest picture, we will need to identify some initial conditions. But this can be circumvented by a different yet related method, the so-called Heisenberg picture. Here we start from the same expression of the expectation values, but then focus on the center of this expression, where we have the operators. We can combine all of these operators, including the time evolution operators, into one and interpret this as a new time-dependent operator. We denote this new operator with the subscript h, which indicates that this is the so-called Heisenberg picture. And so this new operator is in general time-dependent, even when the original operator A is not time-dependent. And now we can study how this operator changes over time. Well, for this we again apply the product rule and the Schrödinger-like equations for the operators u and u dagger, just in the way as we did in the derivation for the Ehrenfest theorem. And the result indeed just looks very similar to this. In particular, it involves the commutator between the Hamiltonian and the operator A itself. Both of these operators are then evaluated in the Heisenberg picture. Just as before, we here have an additional term when the original operator A was already time-dependent. And so with this we can study aspects of the dynamics of the quantum system without reference to any quantum state at all. We of course need such a state in order to convert this information into observable physical properties, such as expectation values. But according to the expression at the very top, we can evaluate these expectation values just using the initial state. And so these characteristics of the Heisenberg picture, that the operators depend on time but the states do not, are in contrast with the Schrödinger picture that we have applied so far. So let us finally turn to an example to illustrate these two methods. So this is our second example overall, and for this we look at the driven harmonic oscillator. Here, the Hamiltonian of the normal harmonic oscillator is amended to include an additional term which is dependent on time and linear in position. Classically, this additional term induces a driving force little f of t. And this term then simply appears as an additional term in the equations of motion. Well, this equation can still be solved exactly for arbitrary function little f of t. For instance, one can use so-called Green's functions. Well, the method itself will not be important to us, but the result will be because a very similar equation will also appear in the quantum setting. So here I simply write down the answer and then we can verify whether it is correct. The first two terms coincide with the solution of a normal harmonic oscillator without the driving. The driving enters the last term and indeed appears there inside an integral. And in this integral it is multiplied by what is known as the Green's function. The first two terms are known as the homogeneous part of the solution, and the last term is the inhomogeneous part. So let me highlight the Green's function in there. Well, we can check that this is indeed a solution by taking temporal derivatives. Here is the first derivative, where we apply the chain rule to the first two terms, and the Leibniz rule to the last term. What I've written down so far is obtained by applying the derivative to the integrand, and then we have one more additional term which we obtain by applying the derivative to the integration boundary. But this term simply vanishes when we then insert the value of the integration boundary. And so we can proceed to the second derivative, where we encounter a very similar pattern, only that now the term from the integration boundary remains finite. And now the first three terms are just proportional to the original expression for the position, and just in the same way as it appears in the equation of motion, while the last term is just the remaining term in the equation of motion. Okay, so these were our classical preparations, and they were admittedly a little bit lengthy. But this will now make our life very easy when we turn to the quantum mechanical case. Indeed, with the help of the Ehrenfest theorem and the Heisenberg picture, we can then focus on the essence of the quantum dynamics. We start with the Ehrenfest equations of motion. These involve the expectation value of the classical force. But because this is now at most linear in position, there is no difference between this expression and the force evaluated at the expectation value of position itself. And so no new terms appear due to the expectation value of the force. We call this a closed set of equations. And on top of this, these equations are then formally identical to the classical equations of motion, so the equations that we have just solved. And so this further emphasizes how similar the quantum mechanical oscillator behaves to the classical oscillator. And this then even applies in the presence of a driving force. Well, let us then see how this is borne out in the Heisenberg picture. Here we could just proceed as before based on position and momentum, but from this we would not really learn anything new. So let us therefore adopt a different approach, indeed a very efficient one, namely the one which is based on the creation and annihilation operators. As a reminder, these operators are combinations of the position and momentum operators, as specified here for the annihilation operator. And with these, the Hamiltonian of the harmonic oscillator takes a very simple form. And this form does not become much more complicated when we then include the driving. The key strength of this approach is the very simple form of the commutators given here. And this form also holds for the Heisenberg variants of these operators. And so from this we can then write down the Heisenberg equations of motion. And indeed we just need a single one, because the equation for the annihilation operator only involves the annihilation operator itself. And because this is now a first-order differential equation, this can be integrated by very standard methods. So I again just give the result here that you can check very easily for yourself. With this result, we can then revert to the position operator, which just involves the sum of the annihilation and the creation operators. And when we express this in terms of the initial conditions, which just are our original position and momentum operators, then we obtain this expression here. And now this again looks formally identical to what we obtained in the classical case. And so our preparations really paid off. Well, in this example we could solve the equations exactly, but in many cases we can only do this using approximations. And in order to illustrate the nature of such approximations, we now turn to the second general discussion, which solidifies the concept of transitions.